Good afternoon, everybody. Uh, I wanted to say about the field patterns in a rectangular waveguide. But before going to the field patterns, we should recall what are the wave equations in a rectangular waveguide. So the wave equations can also be said as field expressions because any electromagnetic wave is going to have electric field as well as magnetic field, right? So the wave equations can also be called as field expressions. And we are going to see what are the field expressions which are available in a rectangular waveguide. Okay, so a rectangular waveguide, the name itself denotes that it is having a rectangular cross section. Okay, so if it is a circular waveguide, it means that the cross section is going to be circular, which means it is a cylindrical waveguide. Okay, so we'll see a rectangular waveguide today. So in a rectangular waveguide, I have three dimensions: x, which is the cross section's length; y, which is the cross section's width; and we have the distance or the direction of propagation of the wave, which is z. So when I send an electromagnetic wave inside this hollow waveguide, the electromagnetic wave is going to pass along the z direction. So when the electromagnetic wave is passing, it is going to have some field, right? It should have electric field as well as magnetic field. The electric field and magnetic field will be present anywhere, we do not know, right? But it will have 6 components, which is along x direction it will have electric field and magnetic field, which is denoted by Ex and Hx. Along y dimension also I will have the electric field and magnetic field, which is denoted by Ey and Hy. Along z dimension also I will have the electric field and magnetic field, which is denoted by Ez and Hz. So totally how many components are there, or how many fields are available? 1, 2, 3, 4, 5 and 6. So I have Ex Hx, Ey Hy, Ez and Hz. So I have 6 field expressions or 6 wave equations, and we already derived these wave equations for a general electromagnetic wave. I hope you remember. So if I take the wave equations, I have 6 components, right? What are they? Ex, Ey, Ez, Hx, Hy and Hz. So these 2 components are the components along the direction of propagation. Okay, and these 2 components are along the cross section. So I have derived it as Ex, Ey, Hx, Hy in terms of Ez and Hz. So this derivation we already saw by deriving it from Maxwell's 4 equations, right? So it is a continuation of this. So the general wave equations were obtained from those. So Ex, if you recall, it is minus gamma by h square. What is this gamma? It is the propagation constant, okay? So minus gamma by h square dou Ez by dou x minus j omega mu by h square dou hz by dou y. So Ey was minus gamma by h square dou Ez by dou y plus j omega mu by h square dou hz by dou x. Hx is minus gamma by h square dou hz by dou x plus j omega epsilon by h square dou Ez by dou y. Hy is minus gamma by h square dou hz by dou y minus j omega epsilon by h square dou Ez by dou x. So I hope you remember. So we have covered 6 field expressions here. If you see here, Ex, Ey, Hx, Hy, all these have the expressions in terms of Ez and Hz. Okay, so 6 field expressions are covered here, and these are the general wave equations for any electromagnetic modes. So I know in a rectangular waveguide, I have TE modes existing and TM modes existing. Do I have TEM modes existing in a rectangular waveguide? No, I don't have TEM mode existing. We'll see why. So if it is a TE mode, it means that if I consider the rectangular waveguide, along the direction of propagation Z, if it is a TE mode, the electric field along the direction of propagation will be 0. Okay, which means for a TE, Ez is 0. For a TM mode, magnetic field along the direction of propagation is going to be 0, which means Hz is 0. For a TEM mode, both Ez and Hz are going to be 0. So here Ez is 0 as well as Hz is 0. So if you substitute these Ez values in these expressions, so for example, these are the general wave expressions I said, field expressions, right? So if I want to find out the wave equations for TE mode, I know definitely Ez is going to be 0. So what happens? This term becomes 0, this term becomes 0, this term becomes 0, and this term becomes 0. I do have Hz values for TE. Okay, so if you see here, what are the other components which are present for TE? Ex, Ey, Hx, Hy. Ez is 0, so I will have Hz. Okay, so for TM, Hz is 0. So now this term becomes 0, this term becomes 0, this becomes 0, and this becomes 0. So if you see here, Ex, Ey, Hx, Hy, and Ez is available here. Hz is 0. Okay. So if I take TEM wave, you see both Ez and Hz is 0. So all the terms become 0. If all the terms is becoming 0, Ex, Ey, Hx, Hy also become 0. So none of the field expressions are existing in a rectangular waveguide for TEM mode. That is why I said TEM mode do not exist in the rectangular waveguide, but we have TE and TM modes. So if you remember the derivation, we also derived the wave equations for TE mode separately and TM mode separately. I hope you remember. So let us recall that also.